Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of Organic Chemistry Lectures and Solutions to Homework Problems. In this Scribblecast lecture, we are introducing our first reaction mechanism, SN2, Substitution Nucleophilic Bimolecular. In an SN2 reaction mechanism, we have an organic substrate, which I'm going to draw as chiral, just so we can determine what happens to chiral centers. And our leaving group we'll use as the halide bromide. Our attacking nucleophile will be hydroxide in this case. What happens when the hydroxide attacks is that it begins to form a bond to the carbon. As this happens, the bond to bromine begins to break. The H, methyl, and ethyl groups go to the positions of a trigonal plane. And then what we have, we could write in bond forming, and here I can write bond breaking. So bond forming, bond breaking, the negative charge is transferring delta minus, transferring from the hydroxide to bromide. The carbon has become sp squared hybridized. So effectively the hydroxide, by donating electrons, and the bromide are fighting over this 2p orbital. The carbon's got sp squared hybridized, and so there's a pure 2p sideways here that they're fighting over. So if I wanted to, I could draw in a 2p orbital here. And this is my 2p orbital that they're fighting over. This structure is called a transition state. So we have a bond forming and bond breaking 5-coordinate transition state where carbon has gone sp squared. By the time bromine has completely left, our HO has attached to the carbon. The bromide has left, so there's plus a Br minus here. This reaction mechanism is the SN2 reaction mechanism. It has certain key features that we're going to look at. Now, what I'm going to do is write out all the key features here, and then we will go through and discuss them one at a time. So what are the key features of this reaction mechanism? Well, the first key feature is that the reaction is bimolecular. The proper definition of bimolecular is that the formation of the transition state in the rate dependent step, or rate determining step, is determined or dependent upon the concentration of both reagents, or two reagents. Let me say that again. The rate of reaction of the formation of the transition state of the rate determining step is dependent on the concentration of two reagents. Rate of reaction is how fast the reaction goes. Transition state is this 5-coordinate transition state we see before you. Rate determining step simply means a slow step. In this case, there's only one step. So when we say the reaction is bimolecular, what that means is if we increase the concentration of hydroxide or increase the concentration of alkyl halide, the reaction speeds up. And we'll talk about why that is the case shortly. So it's a bimolecular reaction. Point 2. The reaction involves nucleophilic backside attack. Point 3. Chiral molecules undergo inversion. So chiral molecules undergo inversion. Note that the hydrogen, methyl, and ethyl groups are now pointing in the opposite direction. Chirality is inverted. We'll talk more about that once we're finished listing all the key points. It is a one-step concerted process. It's a single-step reaction. Everything happens at once. Point 5. It involves a 5-coordinate transition state. That just means 5 groups bound to the carbon. A 5-coordinate transition state. So we're going to have to look at that. 6 is there's no isolable intermediates. 7, there are no rearrangements. 8, methyl is faster than primary, who's faster than secondary, who's much faster than tertiary, because tertiary doesn't undergo this reaction mechanism. And the last key feature really doesn't get a number 9. It's just listing what this is favored by. So this mechanism is favored by stronger nucleophiles. You can write this down. It's favored by stronger nucleophiles and lower reaction temperatures. It does show little or no solvent effect. Okay, so let's talk about each of these key features, starting with number 1. Well, leaving the reaction up, the reaction is bimolecular. And actually it makes sense that it would be bimolecular. In order for the nucleophile to attack the carbon, the 2 molecules must collide. Such molecular collision would be expected to increase in occurrence the more crowded it is. We can increase crowdedness by increasing concentration, either of the organic substrate, the alkyl halide, or of the hydroxide. Increase the concentration of alkyl halide, it's more crowded, there should be more collisions with hydroxide, the reaction rate or production of the alcohol should increase. And actually, it is observed to increase. Increase the concentration of hydroxide will increase rate because more hydroxide means more chance of collision, means it happens more often per unit time, means it happens faster. This is experimentally observed. Upping the concentration of either group speeds up the overall rate. Because both speed up the rate, reaction is said to be bimolecular. Now, it is important that you understand you speed up the rate of the rate determining step. In this case, there's only one step, so it's not a problem. Point 2. Again, it's pretty obvious. The hydroxide attacks the backside of the carbon. It attacks on the side opposite the carbon-bromine bond. It attacks the side exactly opposite the bromine, because in so doing when carbon rehybridizes to sp², the hydroxide is fighting for an orbital where it can create a bond, and the bromine is leaving and surrendering that orbital. So we observed nucleophilic backside attack on the side opposite the carbon-bromine bond. If we look at the product, we see the chiral molecule. In this case, if I prioritize 1, 2, 3, this guy is S. The chirality now, 1, 2, 3, is R in the product. So taking a chiral molecule will result in inversion. Now, don't think that you have to have S always go to R. if there was something in the group that was attacking that made the prioritization switch so that hydroxide wasn't number one priority like bromide is, it would be possible to get inversion but have the inverted center S give you S. And the inversion, because the prioritization changed, the IUPAC nomenclature looks like it hasn't changed. Nevertheless, the inversion really occurs. So just beware that. Just because S gives you R in this case doesn't mean it always have to. For example, if I replaced the ethyl with a fluorine, if this was not ethyl, bromine would still be number one, fluorine would 2, methyl, this would be still S. But when hydroxide bound the ethyl, which is now fluorine, the fluorine would be number 1. The hydroxyl would be number 2. That would still be S. And the reason is the group that replaced the bromine did not retain priority 1. It became priority 2. So there were the inversion changed the chirality and the prioritization changed. So inversion still occurs, but in that case, when it's fluorine, S goes to S. And you can take a look at that and puzzle over that one. If you don't understand it, don't hesitate to come see me. Okay, point 4. Well, in point 4, we do have a one-step concerted process. A one-step concerted process. Everything happens all at once. The hydroxide comes in and attacks. Carbon goes sp squared. The bromide starts to leave. The groups invert and shift, and you get inversion all in one smooth transition. There's no separate steps, no intermediates. Point 5. Point 5 will take a separate discussion. The 5-coordinate transition state. Let's draw it again. Br is leaving. Our H is up. Trigonal planar, CH3. Well, there's no doubt that the transition state is 5-coordinate. Usually when you draw a transition state, you put it in square brackets to indicate that this molecule is not really a molecule. It doesn't exist. It's just a transition state. We have a delta minus, delta minus. We have our bond breaking. We have a bond forming. Carbon's sp squared. And this is called the transition state. Double dagger at the top simply means transition state. It's 5-coordinate because there are 5 groups. What does the word transition state mean? Well, a transition state has no finite lifetime. It doesn't exist as a separate entity for a period of time. Now, that no finite lifetime can be debated, and we'll talk about that debate in a moment. But let's continue with the definition. A transition state has no finite lifetime, but it is the highest energy structural form traversed in the smooth transition of reagents into products or reagent into intermediate. So let's say that again. A transition state is the highest energy structural form traversed in the smooth transition of reagents into products. What do you mean, highest energy structural form? Well, suppose I made a graph. And on this axis we had energy. This bottom axis could be time or progress of the reaction. So the progress of the reaction is in that direction. We've got our axis continuing. Over here, we have our reagents. Over here, we have our products. Now, in every reaction, you can measure the change in energy. That if I draw a dotted green line here, this difference in energy, right here, would be what we call delta H, or the change in enthalpy. Now, on the way, there will be a rise in energy. This rise in energy is caused by the repulsive forces caused by the hydroxide and the bromine, both crowding around and fighting over this 2p orbital. At some point, you will reach a peak in energy. As the bromide begins to leave, the energy will begin to fall and you'll get your product. But this point, right here, that's the highest energy point. That is where the transition state occurs. So in the definition, when we say that it is a transition state has no finite lifetime but represents the highest energy structural form, it is at this highest energy form that we draw the structure. When the two groups are both fighting over this 2p, you have a 5-coordinate transition state, 5 groups around it. There's too much electron density around the carbon. This is real high energy. It does not last long. In fact, this energy is often called the energy of activation, EACT. EACT is the energy you have to put in to get the reaction to go. The reaction may be exothermic, but if it has a high energy of activation, it won't happen. The most common simplistic one is wood not spontaneously bursting into flames. We know oxygen plus carbon in the form of wood leads to combustion, fire, and heat energy is released. It's exothermic, so why are not trees spontaneously combusting? It's because to initiate the reaction, you have to put in a certain amount of energy of activation. All reactions have some kind of energy of activation. Sometimes it's large, sometimes it's small. And at the top of that energy activation, at that peak, in sometimes yielding products, sometimes yielding an intermediate, you find a transition state. And it's the highest energy structural form. Now, why do I say no lifetime? Well, in the early days, when this theory was being developed, these items were so short-lived, they literally could not be measured. But technology has improved. We can now analyze things at the femtosecond or attosecond timescales. And when we're looking at extremely short-lived species, we actually can take absorption spectra at such short time lengths that it's almost as if these structures are frozen in time. But if our ability to measure also matched our ability to detect, we would quickly see that the molecule spends no time sitting in this form, but rather actually undergoes a smooth transition through this form. It's a lot like a basketball player who slam dunks a basketball. And when they're floating in mid-air, if you take a high-speed camera, you can snap a picture that makes it look like they're frozen in mid-air. But you'd never say he's spending significant time in that position. In actual fact, if you could measure it, the very next high-speed photo, he would have changed his position and structure slightly as he's releasing that ball into the basket. And the same goes with this transition state. In the very next instant in time, there's a slight difference where the bond, I can't believe I messed that up. The bond forming, that should be bond forming. Sorry about that. The bond forming to the oxygen is a little shorter, a little more bond, and the bond breaking, the bromine's a little further away, a little more on its way to becoming free bromide ion. So when I say no finite lifetime, I am suggesting that this species doesn't hang around for a period of time. More important than no finite lifetime, though, is the fact that it's the highest energy structural form. Right? Okay. The other features of the 5-coordinate transition state, again, OH is bond forming. We show which bonds are forming. We show which bonds are breaking. We show where the delta minuses are, or delta pluses if there are any. And we show the sp squared state. We show the movement of electrons, the making and breaking of bonds. Excellent. Now the next key feature, if you look back, was that there are no isolable intermediates. The reaction, this really corresponds well with number 4, and it's stating number 4 in a different way, 0.6. No isolable intermediates means it's a smooth transition. There's a single transition state and you get products. We don't stop at any species that floats around for a while and then moves on to create the products. Point number 7, no rearrangements, will be discussed in the next reaction mechanism when we actually look at an example of rearrangements. Point 8 is interesting. Point 8 simply states that methyl reacts faster than primary, which reacts faster than secondary, which reacts faster than tertiary. In fact, tertiary typically does not go this mechanism. But I guess if you don't go it, that means you're pretty slow. And the question we can ask is why? Why is methyl faster than primary, faster than secondary, faster than tertiary? What you see before you is what you would see if you were looking down the backside, okay, the backside of all of these molecules. A methyl halide. The big atom in behind is my bromide. The gray group you see is the carbon we have to attack, and the methyl has 3 hydrogens. In my primary alkyl halide, one of the hydrogens off the carbon we have to attack has been replaced with a black carbon to distinguish it, and 3 hydrogens off it, so it's a methyl group. So this is an ethyl bromide. Our secondary alkyl halide has 2 methyls replacing hydrogens, 2 black carbons attached to the gray carbon we have to attack. That's my isopropyl bromide. And finally, the tertiary alkyl halide has replaced all 3 hydrogens with methyl groups, and we must attack the silver carbon. This is tert-butyl bromide, and we're looking at the back side of these groups. So we have to attack those positions. We have to attack that carbon. Now the one thing you notice as we go from primary or methyl to primary to secondary is that this carbon, gray carbon, is becoming more and more obscured. The nucleophile has to get past the junk in the trunk, so to speak. It has to get past the steric bulk that is building up around this carbon. If the steric bulk becomes so great that it totally obscures the carbon, as we see in the tertiary halide case, it can shut down altogether any accessibility to the SN2 mechanism. And when we're doing this, what's really going on is, you remember the energy diagram I had with reagents here and products here. As you go from methyl to primary. These extra methyls are raising the energy of activation until what happens is, in the case of tertiary, this energy of activation gets so large that there are other pathways it can go that are lower energy. And so tertiary doesn't react this way. So the rate, or what we've listed as key feature number 8, is a direct consequence of key feature number 2, which was nucleophilic backside attack. The requirement of backside attack means we have to get past the groups surrounding the carbon, the gray carbon. And you can see how difficult that can really become. Now, the last point is that this reaction is favored by stronger nucleophiles. Stronger nucleophiles come in quickly. Because they come in quickly, this will prevent alternative mechanisms from happening. And so you'll go through this one-step concerted process, forming the transition state quickly. It's also favored by lower reaction temperatures. Lower reaction temperatures will help avoid those mechanisms that are favored by higher temperatures. And so we favor the substitution by using lower reaction temperatures. The last point to make really depends on how you look at the mechanism. And that is, there's little or no solvent effect. Well, I thought nucleophiles were slowed down in their attack by aprotic solvents. Well, that's true. The aprotic solvents will slow down the nucleophilic attack, but because we're using strong nucleophiles, they tend to attack the organic substrate fairly quickly. And they do show an effect, but it is smaller. The next mechanism we look at, we will see much larger solvent effects. And because it has larger solvent effects, we can actually favor that mechanism over this one by changing the solvent. All right, well, there you have it. It's SN2, our first reaction mechanism, substitution, nucleophilic, bimolecular. I think this would be a good place to stop. I'm Dr. Brian Lloyd. This is my Scribblecast. We'll be continuing our next Scribblecast lecture by looking at another substitution mechanism, the SN1.